said that I need to wait. So good afternoon. Welcome to the CERIAS Security Seminar Series. So today is my great pleasure to introduce Dr. Ariel Freeman from University of Chicago. Ari is a assistant professor of computer science at Chicago. His research lies at the intersection of computer security and distributed systems. He is presently focused on finding new ways to protect the security and privacy of users of cloud-hosted services. His interests also include software and network security, data privacy, anonymity, and electronic voting, as well as the interaction between computer security, law, and public policy. Previously, he was a postdoc researcher at the CERIAS department at the University of Pennsylvania, and he received his PhD in computer science from Princeton University in 2012. Ari?
Yeah, thanks so much. So good afternoon. As you said, I'm Ari Feldman, and I'll be talking about verifying computations with and without private state, and I'll get to what that is later on. And the material in this talk is based on joint work with professors and students at the University of Texas at Austin, as well as the University of Pennsylvania. So as computing permeates ever more aspects of society, we increasingly participate in complex systems where we rely on computation performed by others. So this includes cloud services that are pretty familiar, like Amazon Web Services, Microsoft Azure, the various Google services, and so on. It also includes Internet of Things devices, these so-called Internet of Things devices, which include the thing on the left is a smart meter, these devices that track how we drive to decide how much we should be billed for auto insurance, navigation devices like GPS navigation devices. And another perhaps less recognized example of relying on the computation done by others is research studies, often based on common data sets, such as those from the US Census Bureau or those from other data repositories like IDASH, which is a repository of biomedical data at UCSD. So we rely on computation by a lot of different parties, and these parties may not have the same interests that we do. Sometimes their interests are even at odds with us, and so this leads to a number of problems. So it's well known that this leads to privacy problems. A lot of people have talked about this. This has gotten a lot of attention. There have been breaches by external attackers to cloud services. There have been changes in privacy policies of the various entities that we interact with and who hold our data, potentially using our data in ways that we didn't expect. There's the possibility of government pressure and surveillance even. There's also the risk of accidental leaks due to bugs or even de-anonymization of the results of release data. So I'm not going to talk that much about most of these threats to privacy except for accidental leaks. However, I have worked on them in the past. What I will be talking about mainly today are sort of another class of problems that arise when we rely on computation done by others, and that is threats to the integrity of our data and the computations that are performed on it by these other parties who we rely on. And the reality is that these computations can fail in Byzantine ways, leading to arbitrarily corrupt results. And these faults could be malicious. These third parties might have the incentive to simply behave incorrectly, deviate from correct execution. But of course, these faults could also be non-malicious. They could be a result of corrupt inputs. They could be a result of misconfiguration, of software bugs, or hardware faults. And right now, I argue that the main tools that we use to mitigate these are mostly sort of non-technical. They're legal or market-based. So we have laws, we have government regulations on the handling of data, we have court decisions, and then we have promises made by these various entities, privacy policies, service level agreements, and so forth. But I'd argue that these non-technical methods aren't enough. And in particular, they aren't enough for dealing with problems of integrity. And the reason is because in many cases, misbehavior by these parties is very hard to detect. And if you don't even know that the parties are misbehaving, either intentionally or not, these non-technical methods can't work well. You can't really sort of have an enforcement mechanism if you don't even know that things are going wrong. So for example, if you outsource a computation on a large amount of data, that may take hours, this computation, and then get back a result, how do you know that the result was actually computed correctly? So that you would be able to enforce some kind of, legal mechanism or some kind of contract or something like that. And so as an alternative, one of the main things that I work on is the idea of designing systems for verifiability. That is, assuming that system participants are untrusted and providing the participants with enough information to check that others are executing correctly rather than simply relying on their promises. And one of the other things that I'll be talking about today that is nice about designing systems for verifiability is that it opens the door for new applications, such as that this verification can be done in zero knowledge, something that wasn't possible before, which means that you could verify someone else's behavior even if you didn't necessarily know the inputs to the computation that they performed. And I also want to note that what I'm going to be talking about, this method of verifying computations, is different from program verification. So program verification is concerned with determining whether a particular program matches a specification, whereas what I'll be talking about today is given that you have some code, and given that assuming that you know what it does, if you give it to someone else, can you verify that they have executed that code correctly? And so I'll be talking about two systems in this vein that I've been part of, that I've worked on with my collaborators. The first is called Pantry, which is a system for outsourcing computations and verifying the results, verifying that some other party who you outsource the computation to executed it correctly. That is sometimes practical, and I'll get to what I mean by that. And the other system I'll be talking about is called VerDP, which was at Eurosys this year, which is about how you do verifiable and privacy-preserving data analysis, such as in the case of a research study. You want to convince others that the results of your research study are correct, so while still preserving privacy. So let's start with Pantry. So the goal of Pantry is to be able to outsource computation to an untrusted provider running a set of untrusted servers. So this is, like the Amazon EC2 style case. And there are a couple of goals that we had for Pantry. The first is that we wanted it to be practical, at least, for some uses. And so one of the most basic standards of practicality for outsourced computation is that it's worthwhile for the client. That is, that it's actually cheaper for the client to ask someone else to do the work than to do it themselves. Because obviously, if you don't even meet that bar, then unless you're adding some other feature like zero knowledge, there really isn't any reason to do it. The other thing is we wanted to support realistic applications such as MapReduce computations and database computations. And finally, we wanted the system to be designed for verifiability. We wanted it to be efficient for users of these services to be able to efficiently verify computation results. So given this problem domain, there are a number of possible approaches that might come to mind. The first is to sort of audit random samples of the computation results. Maybe you sort of re-execute the computation on sort of portions of the input or parts of the computation. But it's hard to catch small errors without doing a lot of auditing if you just audit random samples. It's kind of a needle in the haystack problem. Another alternative is to kind of do a BFT style design and run multiple replicas of the computation. But this assumes that the faults are uncorrelated. Another approach would be to take advantage of trusted hardware and use remote attestation to have the trusted hardware attest to the fact that some particular code is running on the remote system. But of course, that requires an additional assumption. And you can also create special purpose protocols, which may be efficient. They may even be more efficient than general purpose verifiable computation, but they're difficult to create and to prove correct. And so what we want is something that sort of covers the broadest possible set of programs that we can conceivably outsource. And so we want something that's general purpose, and we want something that has unconditional guarantees in the sense that we only rely on, let's say, cryptographic assumptions rather than assumptions that, for example, the remote party runs some piece of trusted hardware. So in theory, we know how to do this. We can just use probabilistically checkable proofs. And there are PCP-based argument systems where a client has some input X and some function F that they want to outsource, and they send those things to a server, and the server responds with a result Y, which is purportedly equal to f of X, as well as a proof pi that that is indeed the case. So in principle, we could do this, and in fact, the PCP theorem states that the client only needs to inspect this proof in a constant number of locations regardless of the computation. Unfortunately, just simply applying this to the problem doesn't work so well in practice. The sort of traditional, as in, maybe prior to the past 5 years, PCP-based systems are really slow, and I mean really slow. So for example, verifying the result of a 500 by 500 matrix multiply would take more than something like 500 trillion CPU years. Fortunately, within the past 5 years, there have been a number of advances in this area of verifiable computation that have led to many orders of magnitude of cost reduction and have yielded built systems that, for example, have compilers that compile high-level languages like C into representations that are amenable to doing this kind of proof-based verifiable computation. And a number of different groups have worked on this problem, and the system that I'm going to discuss, Pantry, is based on two of them, Zatar and Pinocchio. So what does Pantry do? Well, there's another problem with PCP-based systems, with prior PCP-based systems, and that is that they were stateless. That is, that whenever you wanted to outsource a computation, you had to send all of the input from the client to the server, along with your function, and the output had to be sent, all of the output had to be sent back to the client, which is obviously sort of not a practical situation for the sort of outsourced computations on sort of large data sets that we're hoping to be able to do, such as MapReduce processes, as well as database queries and that sort of thing. It's really impractical to pay that kind of network cost. So as a result, we need to do something more. And so what Pantry does is combine recent advances in verifiable computation with untrusted server storage. So what it does is that it gives the server access to some untrusted storage, some storage that the client does not need to trust. And then the proof of correct computation that the server returns to the client not only states that the function was evaluated correctly, but that all reads and writes to this untrusted storage were done correctly. So all of the reads actually fetched data that was really there in the untrusted storage, and all writes actually wrote the correct values correctly computed by F back to the storage, so that, for example, if a subsequent computation accessed it, you could actually say something as the client about what that storage contained. So to explain how this works, I just want to provide some background about verifying a computation, and in particular the way that Zatar and Pinocchio work. So this process of verifying a computation basically proceeds in 3 steps. First, the client compiles the program to a circuit representation which implements a series of algebraic constraints. There's basically you can think about it as a system of equations where each equation corresponds to one gate in the circuit. Then that compiled representation is sent to the server, and the server finds a satisfying assignment to these constraints. That is, finds an assignment to all of the variables in those equations to make them all hold simultaneously. And then finally, the server proves that it knows this satisfying assignment to the client. So let me explain how these 3 steps work in more detail. So the first is actually making and satisfying these constraints. So for any program written in a high-level language, basically each program construct is converted into a series of constraints. So suppose we had this simple program, add 5, which simply takes an input x as a parameter, adds 5 to it, and returns the value. So you can compile these into these 2 constraints on the right over there. And these constraints are chosen by the compiler so that they are satisfiable if and only if the output is correct given the input x. And so basically the compiler for each potential program construct creates an equivalent set of constraints. So suppose you had an input x. Well, then if the server computes correctly and outputs y equals 9, it's possible to satisfy both of these constraints simultaneously. But suppose that the server claims that the output y is 10, then it's not possible to satisfy these constraints. And so therefore, finding an assignment is tantamount to correct execution. It's only possible to find a satisfying assignment if and only if the program was executed correctly. And this can be done for more complex program constructions. So you can do this for branches and for inequalities and for loops and so on. So for example, if you had this not equal condition, you can represent it as the 2 constraints on the bottom left. And basically you can see that if x1 equals x2, then you have to set y equals 0 in order to satisfy the first constraint. Whereas if x1 is not equal to x2, then you have to set y equal to 1 in order to satisfy the second constraint. And so these 2 constraints, when taken together, make sure that the result of the not equal operation is actually correct. So once this satisfying assignment is found, the server needs to prove to the client that it's actually really done this. So the simplest thing you could imagine it doing is simply sending over as the proof the list of assignments, values assigned to all of the sort of intermediate variables of all of these constraints. But verifying this is actually as expensive as doing the computation over again, because you essentially have a number of constraints that's linear in the size of the computation, and you have to plug in all these values and basically reevaluate it. So that isn't going to work. So instead, what these protocols do is they convert the satisfying assignment into, at least many of these, including Zatar and Pinocchio, they convert the assignment, the satisfying assignment, into a QAP, a quadratic arithmetic program, which is basically a polynomial with an error detection property. And then the client can kind of query this polynomial, ask the server to evaluate this polynomial at a random location, and the response is sufficient to prove that the server does in fact know a satisfying assignment to all of the constraints without actually having to return them all. So these systems have the property that constructing this query is expensive. There is some setup phase, depending on the system. For example, Zatar and Pinocchio are somewhat different, but they both have a setup phase that's roughly linear in the size of the computation. Fortunately, this cost of setting up can be sort of amortized over multiple invocations of the same computation over multiple inputs. The client can provide multiple inputs and get back multiple outputs along with multiple proofs. And indeed, these can be run in parallel, which will be very good for certain applications like MapReduce. So what about the issue of verifying reads and writes to untrusted storage? So in Pantry, the sort of naive way of doing this would be to treat the untrusted storage as kind of a big switch statement, where there is a variable associated with each position in the storage, and let's say a load from storage would just be sort of a switch statement over all of the storage. But this really isn't any good. It's linear. Each load operation, for example, would require a linear amount of work in the entirety of the storage. So instead, what Pantry does is structures the untrusted storage as a block store, where essentially blocks of data of arbitrary size are named by the hashes of their contents. And then it augments C with two new operations. The first, get block, works by giving an input digest or hash D, returns a data block B, which has the invariant that the hash of that block B has to equal the input hash. It also augments C with a put block operation, which takes a block B at input and returns a digest, a hash D prime, that preserves the invariant that digest that's returned has to be equal to the hash of the supplied data, which is then stored in the untrusted block store. So how do you verify these operations? Well, suppose you had this example where there's an input hash D, and then the program performs the get block operation to get the block corresponding to that digest, treats that block as an integer, increments it by 1, and then stores it in Y and returns the result. So this is compiled to a set of constraints which roughly have this structure. So the last constraint is one that you'd recognize. That just makes sure that the increment was done correctly. But what of the rest of the constraints? The rest of the constraints essentially implement the hash function in the form of constraints, and then compare the result of the hash function with the input digest D. So the only way to satisfy those constraints is for the hash to be computed correctly. And if the hash is a good hash function, is a collision-resistant hash function, then this also can convince the client that the correct value was fetched. So you're essentially outsourcing the check that the correct value was retrieved in this one instance to the untrusted server, and rely on the fact that the check has to be computed correctly because it's part of a verifiable computation. So given these tools, what can you do? It turns out that with just C and get block and put block, you can implement verifiable MapReduce. And so the way that works is the client outsources a particular map function to a set of mappers run by the untrusted provider. And it also provides some input hashes of the particular blocks of data that the various mappers are going to work on, along with a query, which is going to be used as part of the proof, is going to be used by the server to generate proofs. So what does the mapper actually do? Well, it calls each mapper basically calls getBlock on the input hash to get the block of data verifiably. Then the map function runs on it, and it produces some output. And then for each of the reducers, a new block is written to untrusted storage, and the digest of that block is actually returned to the client, along with the proof of the correct execution of each of the mappers. Then in the reduce phase, the client turns around and sends those interim hashes of the results of the map phase to the reducer nodes, along with a reduce function and a query, and the reducers get the necessary blocks, run the reduce function, and then outputs the result as another block and returns the digest of those blocks along with a proof of correctness of the reduce phase. And so what you basically have here is that all of the data never needed to be stored with the client. The client only ever saw small proofs and hashes, and yet can be convinced that this data parallel computation was actually done correctly over this remote database with just C and getBlock and putBlock. Pantry can also do other things. You can build verifiable data structures. You can imagine that verifiable blocks contain the hashes of other verifiable blocks, which allows you to build things like verifiable tree-based data structures and indices and that sort of thing. You can represent queries, like, for example, one example of something we did is we used a subset of SQL, and we compiled that into a verifiable program. And so you could potentially have a relational database with indices and query processing, all implemented with C and getBlock and putBlock, and be able to verify the results. However, beyond that, you can also do something that you can't normally do, and that is zero-knowledge verification. So in that case, not only is the storage not in the possession of the client, but the client is not actually allowed to see it. The only thing that the client has access to is a commitment to the contents of the storage. And that commitment, that cryptographic commitment, binds the server to specific values in the storage while still hiding its contents from the client. So, and this will be useful in the next system that I'll discuss. But what's really interesting about that is that the client can be convinced that this potentially complex computation was done correctly without actually needing to know what the data is. So how practical is all of this? Well, there's good news and bad news. The bad news is that the server overhead as compared to unverified execution is pretty high. Even though it's been improved by, let's say 20 orders of magnitude, it's still several orders of magnitude more expensive. You also have this client setup cost, which can be amortized in certain cases, but it's also an obstacle. And finally, in Pantry at least, the programming model is limited because essentially the entire computation has to be static. Loop bounds, array sizes, pointers, and so forth. Although recent work has started to lift this restriction basically by having the compiled circuit represent more of the machine, the program counter and so forth. However, there is good news. Some MapReduce applications are practical today in the sense that outsourcing is worthwhile for the client. C and getBlock and putBlock are pretty expressive, and you also get zero-knowledge verification. So you get capabilities that weren't previously possible. So in summary, Pantry provides sometimes practical verifiable outsourced computation, by combining untrusted server storage with verifiable computation, yielding realistic applications. And it's also nice that it's unconditional and general purpose, in the sense that it only relies on cryptographic assumptions. So now I'm going to move on to talking about the second system that's in this area, and that's VerDP. So the setting of VerDP is that of verifying research results. So in many cases, you have some data curator, we'll call it, like the US Census Bureau, which has some standard data set. Let's say it's about dog ownership. And then researchers come along and want to perform a query over this data set, and they want to publish the results to some readers. So, suppose the researchers do their study, and they say the average number of dogs that people own is 10 per person. So this seems a bit off, and indeed, mistakes and even fraud do happen in the results of research studies. So what do we do about this? Well, the traditional approach is reproducibility. Somebody else, let's say, takes the data set, they perform the same query over it, they perform the same kind of data analysis, they try to repeat it, and they see whether the results match the published results. Unfortunately, sensitive data poses a problem. So suppose that the database is not about dog ownership, but is actually about something more sensitive, like medical data. Then this raises two challenges. The first is that the result itself of the computation, we know this, the result itself can leak information, such as the famous Netflix prize database de-anonymization. The second problem is that the fact that the distribution of this database is limited limits reproducibility. So there's this kind of conflict between privacy and verifiability in the sort of verification of the results of research studies conducted over sensitive data. So what about using differential privacy? So to deal with this first challenge, often what is an approach that has been proposed is to use differential privacy, which basically involves adding some noise to the result that is published so that the privacy of no individual in the database is compromised. And this is good because it provides mathematical privacy guarantees. It provides a methodology for figuring out how much noise you have to add to preserve the privacy of database participants. However, it actually makes reproducibility even harder because suppose that the researcher wanted to make the result some particular value, like 2.5. She could publish this result, and then even if you had access to this sensitive database, you couldn't actually be sure whether or not the researcher was lying, because the researcher could always claim sort of basically plausible deniability and claim that effectively, the sort of unexpected result is simply a result of the particular choice of random noise that was drawn from some distribution. They could blame it on the noise that they had to add. So to overcome the problem with this approach, we propose combining differential privacy with zero-knowledge verifiable computation of the kind that I talked about earlier. And so, for example, the researcher does not choose the noise, so they can't lie about the noise. And then, in addition to publishing a paper, they also prove the result using Pantry. They publish their query constraints along with a proof of correct execution of that particular query over the data. And then anybody who then reads this paper can get the proof and check that the query was executed correctly, even though they don't have access to the underlying data. So there are a couple of problems with this. The first is that if these constraints represent a circuit, you can't just sort of naively take sort of trace the execution of the query that the researcher wanted to do, convert it to a circuit, and then generate a proof, because the very structure of the circuit could leak information about the database if it depends on the database. The second problem is that Pantry is really only efficient, can really only break even in data parallel computations, like the MapReduce example I talked about earlier, when you can amortize the cost of that setup, over sort of multiple invocations of the same program. And so basically, that's what VerDP, our system, does. It combines privacy and verifiability by combining differential privacy and zero-knowledge verifiable computation. But there's some challenges in actually making this work correctly. So the first challenge is that you have to ensure that the results of computations performed in this system are differentially private. And as we'll see, we use a domain-specific query language for expressing queries. The second problem is that we need to achieve structural privacy. That is, we need the generation of circuits, or equivalently constraints, to be data independent, to not depend on the database, so that it doesn't, the structure of the computation doesn't in any way leak information about individuals. And the third is that we need efficient execution, which means we need a highly parallelizable runtime. So what about the first question, ensuring differential privacy? Well, so there's this existing language called Fuzz, and it is a language for expressing queries, and it has a type system such that if the program type checks, then the result of the query can be known to be differentially private. So suppose that you had a database and you wanted to know how many people are over 40. So you could express it in Fuzz with this code, where you basically apply a particular predicate to each row of the database. In this case, the sort of over 40 predicate on the right. Then you split the database based on whether or not that predicate is true or false. And finally, you count one of the two halves of the database, or one of the two portions of the database, and that's how you get your result. And then you add some noise to ensure that it's differentially private, and basically the sort of type system and runtime sort of keep track of the sensitivity of the computation so that you know how much noise needs to be added at the end. So this is all well and good. The problem, of course, is that if you convert this particular sort of pipeline to a circuit, it could leak information about the particular underlying data, because as you can see, the sizes of the sort of two portions after the split are different. And so if you had sort of the number of gates in your circuit depend on that, that would leak information about the database. So, and there are other examples of this. If you had data-dependent loops or recursion, this could also leak information about the database. So to achieve structural privacy, to prevent the structure of the circuit from leaking stuff, we use fixed size intermediate results, static loop bounds and recursion depth, and statically compiled predicates. And if you if you modify the language in the way that we described, then you can actually prove that indeed structural privacy is preserved. The next question is efficiency. And so, as we talked about with Pantry, the expensive part is the proof setup, which has to be done once, for example, by the curator, and proof generation, which has to be done by the researcher and has to be done basically once per execution of a particular circuit, and is several orders of magnitude more expensive than unverified execution. Whereas what is cheap and independent of the circuit size is the verification of the proofs of correctness. So that can be done in milliseconds. And so we have to manage the cost of the sort of expensive part of Pantry. So just simply taking the query we want to do over the database and converting it into a single giant circuit is really far too expensive. It will overwhelm the resources of an individual server. So we have to exploit data parallelism in some way. And so what's nice about this particular language, vfuzz, is it has the property that the predicate is applied essentially to each row of the database individually. And so what you can do is you can essentially divide each phase of this computation, each phase of this pipeline, into multiple tiles that are then sharded over multiple machines. So all computations in this language basically have three phases. They have a sort of they have the application of the predicate to each row of the database, and you can sort of apply it to chunks of the database. Then the results of these predicates are aggregated in a count phase, and finally noise is added at the end. And so each of these shards can be placed on a different machine. It's basically an embarrassingly parallel problem, which is really good because the complexity of Pantry really depends on the circuit size. And so as a result, you only need to generate a circuit that is sort of linear in the size of one of these chunks of the database rather than the entire database itself. It also allows the cost of sort of setting up the proof to be amortized over all of the tiles, all of the parallel executions of the smaller circuit that, let's say, applies to different tiles of the computation. Now, what about passing values between phases? So now that we're actually dealing with multiple computations, some executed as phases, some executed in parallel, we need a way to sort of connect the data between them. And so effectively, there are a series of cryptographic commitments. Each phase generates a set of commitments to the remotely stored data, which the readers of the paper never get to see. And then these commitments are used to sort of bind the researchers to particular data as the input to the next phase. So the last thing I want to talk about is how well this works in terms of its efficiency. And there are a number of questions that you can ask: the efficiency of proof generation, the efficiency of proof verification, the scalability of the system to sort of larger databases. And so these are the things that I'm going to be talking about now. In the paper, we also talk about the efficiency of proof setup as well as some micro benchmarks. And so in order to figure out how well this actually works, we did a couple of different queries which are sort of common in the differential privacy literature. And we outsourced these computations to a bunch of EC2 instances. We used 32 EC2 instances with a lot of RAM. And in particular, they had some fancy NVIDIA GPUs, which can be used to accelerate the cryptography of the verifiable computation system. One thing that's notable, though, is despite the sort of hefty specs of these machines, they only cost about $2 per instance per hour. So to evaluate this, for proof generation, we estimated the time that it would take for the prover to run on various queries and various sizes of input databases. And as you can see, even with this given level of parallelism, it takes a few hours and only needs to be done basically once before publication. Like, it's not like when you're sort of playing with the data, figuring out exactly what query you have to do. You need to actually do this. You really only need to do it once before publication. And experiments, like we sort of actually did some experiments to verify our cost model. These are represented by those dots, and our actual results were within 3.3% of our projections, and these experiments cost $64 and $128 respectively. Now, what about proof verification? So proof verification is very fast. Each proof, and so now there are multiple proofs because there are these different tiles, but each proof is only 288 bytes and takes milliseconds to verify. So in all of our examples, basically it only took even for our sort of most intensive example, only took less than 3.5 seconds to verify the results. So finally, we were interested in the scalability of proof generation. So, if you wanted to pay more for, let's say, more instances, could you do better? And the answer is that proof generation is actually highly scalable. The work that you actually need to do to sort of prove that you've done a research study correctly scales very well with the number of rows. So for example, if you had 1,000 machines and a 2 million row database, it would take about 100 minutes to generate a proof. So that, at a cost of sort of $2 per instance per hour, and considering that it only has to be done once, it's probably a small part of the research budget, this sort of last step of publishing the proof. And so we believe that, you could actually do this in a lot of cases. And so to sum things up, VerDP enables this interesting combination of privacy and verifiability by combining differential privacy with the verifiable computation machinery that I talked about in the first half of the talk. And vFuzz queries that type check, it provides this nice query language that are provably differentially private and provably structurally private. And the system is in fact, scalable and relatively affordable. It's a relatively small percentage of the sort of research budget that you would have. And we believe that you could do similar things in other applications. Like, for example, suppose that you had one of these devices attached to your car that sort of tracked your driving habits. But you didn't want to reveal, that sort of detailed, sensitive data about how you drive or where you drive to the insurance company. So what you could imagine happening is that your car would sort of provide sensitive driving data to this device, and the insurance company would provide its billing formula, and then the device would return differentially private statistics about your driving, along with a proof that the billing formula was actually correctly applied. So the final answer you get about, let's say, how much you should pay is actually correct. So to conclude, I'd argue that it's possible to build general purpose systems designed for verifiability. And I think it's necessary that we do this because we are increasingly relying on computation done by others. And legal and market-based enforcement, I'd argue, are not enough on their own. And indeed, these sorts of mechanisms can complement them because essentially they provide evidence whether or not these third parties are actually doing what they say they do. It also enables the possibility of new applications that might not have been previously possible due to the risks. The ability to, for example, prove things about databases that you're not allowed to see is sort of a very interesting capability. And so that's all, and I hope we have a little bit of time for questions. And thanks for listening, and thanks for inviting me.
So my question is, Have you thought about further optimizing the execution performance of these verification tasks? For example, by exploiting some of the parallelism that is intrinsic in the verification to make it even more efficient.
So to speed up proof verification?
That's right. Yeah.
I haven't looked at that. I mean, it might be possible to do it. I mean, so one of the issues is that like each of the even though the circuit is the same, the inputs are different, and so so certain aspects of the proof are going to be different. I mean, one of the things about the proof is that it's already so small because it's already kind of independent of a lot of the it's already independent of a lot of the computation. There's already so much that the client doesn't already know. So I'm not sure what approach you would take, but there might be something you can do. Certainly on the server end of things, there have already been improvements since we built the system. For example, one of the most expensive aspects of VerDP is that each phase has to commit to the results of the phase, and then the next phase, each sort of tile of the next phase has to decommit so as to prove that that phase is using the same data as the preceding phase. And so what we did in VerDP is we actually implemented the cryptographic commitment in C and compiled that to a verifiable computation. But if you specialize the proof machinery, as a recent paper from earlier this year did, sort of building commitments into the proof machinery, you can actually do the process of kind of chaining multiple verifiable computations together much more efficiently. So like that would actually lop off a big chunk of the cost of the system that I just talked about.
So very interesting talk. I had two clarification questions. In Pantry, I did not understand what do you mean by this server. We don't trust him for doing correct computation. And then you talked about untrusted storage. So I didn't understand the difference in terms of the assumption that you're making on the server as compared to the storage from the client's perspective.
So from the client's perspective, it actually doesn't matter, whose storage this is, like whether it's actually the same whether it's the same party who holds the storage. Maybe it's just the same server who also has the storage. Because effectively all the client cares about is that there's some continuity between, let's say, some initial commitment to what the initial state of the storage was and sort of all of the subsequent computations. So for example, you know that every value that was read from that database and subsequently used in the computation can actually be tied back to that initial commitment. And similarly, any writes that happened really did update the appropriate portions of that storage. You can even have, as VerDP does, the system output a new updated commitment that the client can actually trust. So the client actually doesn't need to care who holds the storage. They just know that all sorts of sort of corruption might have happened in the storage, but the program verifies the contents of any reads that are then used in the computation. But from the server's perspective, this storage could actually not even be run by even somebody else. You could imagine some block storage run by some other party, and all the server does is sort of do regular get and put operations on that block store. And as long as that block store continues to service requests, it will work, and the client will be able to actually take care of making sure that the contents is correct, because essentially all of the checks are built into the verifiable program.
Okay. And the second thing was, it's also short, but that's regarding VerDB. So here the model is there is a database. I, as a reader or somebody who's looking at the answer, has no idea about what is the database. So how can I be sure that you're taking care of all the validity and integrity, that all the records are used by computation and stuff like that?
Well, so that's why I think that the sort of most realistic setting for using something like this is where there is a data curator with some standard data set, like the Census Bureau or one of these biomedical data repositories, where essentially the data was collected, let's say, by someone other than the researchers. So they can't, let's say, cherry pick the data set in order to get the results that they want. And so then you could imagine that this data set was collected in advance of the researchers asking to do the study. A public commitment was published to it, long beforehand. The sort of data set was not chosen with that particular query in mind, and multiple studies could be done on it. So I think that's a way to that's a potential way to deal with that problem. And then the program itself, could be structured so that it's clear that it actually sort of touches every record, and those are tied back to that commitment.
All right, so in the interest of time, let's keep the other questions offline, and let's thank Ari one more time.